The objective of this video is to practice calculating induced voltage and currents in an asynchronous cage rotor and the corresponding air gap fields. We're not going to introduce any new theory in this video. Rather, we're going to work through a long series of examples of analyzing induction motor rotors based on what we've developed in our video lectures so far. And to begin, I want to review key results from these videos. You'll see in the top right, I've drawn our cross-section of our induction motor and added our reference for the rotor angle theta mech, which is again indicating the location of slot 1. And I'm also showing our rotor angle, and I'm also showing our general reference frame for any angle in the air gap as being alpha off of horizontal, and our rotor reference to that same angle as being alpha with a superscript r. Okay, so now down below here I've written a summary of the key results of these videos, but I've changed them in a slight way. Instead of having all of these results in terms of VP, I'm expressing them in terms of N. And that's something that we're going to do in this video only. The reason for this is that I'm trying to acknowledge that the squirrel cage rotor does not know how many poles the stator has. And so, therefore, in the examples that we're working through in this video, we don't know what the number of poles of our motor is. Rather, we just say that we're going to magically create a field with a harmonic value of n, or with a pole value of n. And we're going to see how the rotor behaves in response to that. So, keeping this in mind, we can again review that the field of the speed of the field in our air gap is going to be our stator synchronous frequency divided by n. We can define our slip in terms of n, just like we did before. We can then talk about this air gap field in terms of n. And so none of this should be a surprise. This should all be familiar to you from our last couple of videos as well as from the broader course, how we can represent harmonics as n. We've derived in a previous video how we can get the voltage that is in any slot of our rotor, and we denote this in the transient domain as a lowercase u, subscript r for rotor. I indicates the rotor bar number that we're talking about or we're interested in, so that's 1, 2, 3, 4 all the way around to QR rotor bars, and a rotor bar current. And n is the harmonic that we're interested in over here. And remember that the way we've defined our voltage sign convention is that positive voltage is always up out of the page at us. Negative voltage is assumed at the bottom of the page or beneath the page. Okay, and we've derived an expression for the magnitude of our voltage. And in this case, and this will also be the case going forward in the class, I'm not giving any angle for our air gap field. We're assuming that when omega t is equal to 0, our air gap field is peaking along the horizontal axis. And we're doing this to simplify our nomenclature a bit, and because it's kind of an arbitrary decision to say that it would be peaking at some other location. There's no magnets on the rotor. It was an arbitrary decision to say that this was slot 1, this was slot 2. So we might as well simplify our nomenclature and just assume that our magnetic field is peaking along the horizontal axis at time 0. And that simplifies our voltage expression. We no longer have to worry about this phi b that we defined in a previous video. And so we get this rather simple expression. We can express this in a phasor notation where the angle of the voltage at any slot in here is just rotated in the clockwise direction by the electric spatial separation of that slot. So if we're talking about slot 2 up here, we're just going to have a phasor that's rotated from slot 1 by n times alpha I radians. Moving forward, we can then use this expression here to determine our current. And so here's an expression for our current phasor. It's going to be our voltage phasor divided by our impedance. And we derived in our previous video that our impedance can be viewed as in terms of a resistance and a leakage inductance that vary as a function of the harmonic that we're interested in. And then we can also express this impedance as having a magnitude and then an angle of zeta r. And this angle zeta is going to come up time and time again in this unit. The angle of zeta is, of course, a function of our slip and our synchronous frequency because that appears in our impedance expression. And so finally, we get a current expression in the time domain. And we note that for the rotor current, positive current is assumed to travel out of the page. And that is opposite from the convention that we were using when analyzing stator windings. So this is, again, our choice to use the generator sign convention. And finally, we noted that with our rotor impedance, the impedance goes to infinity if this expression here is equal to 0. Okay, now we're ready to get started on some examples. Our first example is, suppose that we're studying a Q equals 4 slot rotor. I want you to draw the rotor, number the rotor slots, calculate alpha C, and label alpha I in the rotor reference frame for all slots. So please go ahead and give this a try on your own, and when you're ready to see the solution, press play. Okay, so I've got the solution sketched up here. We've got as we said, we have a 4-slot rotor. I've decided to show slot 1 as being aligned on the horizontal axis at this time. Our angular separation for all the slots is, of course, 90 degrees, so we can calculate alpha C as being 90 degrees. And so slot 2 occurs 90 degrees later, slot 3 is at 180 degrees, and slot 4 is at 270 degrees. All right, our next question is, which air gap field pole pairs will not induce current in this rotor? So determine which pole pairs for our air gap field or our stator field will not cause any current to flow in the rotor. Press pause now, give it a try, and press play when you're ready to see the solution. Okay, so again, to avoid inducing current in the rotor, we need our rotor impedance to become infinity. And we've just summarized that this is going to be the case when the sine of n times pi over qr is equal to 0. And that will happen when n is equal to 4 or any multiple of 4. And so we can conclude then that air gap fields with p equal to 4, 8, 12, 16, 20, 24, and so on, when p is equal to these combinations of pole pairs, we will experience no current in this rotor. Okay, the next question. Draw the equivalent circuit for the rotor in terms of the rotor phase impedance, ZRN, the bar voltage UR, and the bar current. Write an expression for the angle of each bar voltage source. Go ahead, give this a try, press the pause button, and press play when you're ready to see the solution. Here we've got our 4 rotor bars, and I've numbered them. Here's 1, 2, 3, 4. And in series in each rotor bar, we've got an impedance source, which is ZRN, so as instructed. We've got our rotor voltage source with the angle indicated for each bar. And so remember that this angle is going to be n times alpha I for every given rotor bar, and as we previously determined up here, so we've got 0 degrees for rotor bar 1, we've got 90 degrees for rotor bar 2, 180 degrees for rotor bar 3, 270 degrees for rotor bar 4, and so we see that directly maps into our voltage phasors. Next, I want you to label the angles on the voltage sources for n equals 1, 2, and 4. Go ahead, give this a try, and resume watching when you are ready to see the solution. I've added our angle for each of these cases, so you can see that this top row right here corresponds to n equals 1. The next row down corresponds to n equals 2, and then n equals 4. And looking at the leftmost on bar 1 for n equals 1, we just simply have the angle that we're seeing in our exponents for our voltage source. We got 0, negative 90 degrees, negative 180 degrees, negative 270 degrees. And I've color-coded bars 1 and 3 in this case because you see that they are 180 degrees out of phase. So bars 1 and 3 look like they belong to the same coil, but are just two coil sides on opposite ends of the coil. So if coil side 1 is at 0 degrees, coil side 3 is at negative 180 degrees, that looks like a single full pitch coil. And similarly, I've color-coded 2 and 4 because they also are 180 degrees out of phase. So effectively, at this harmonic, it looks like we have a two-phase winding where the coils are arranged so that they form full pitch coils. And we can observe a similar phenomenon for n equals 2, only now it's like we have a single phase because coil side, or bar 1 and bar 3 are completely in phase. Bars 2 and 4 are completely in phase. So now it looks like our full pitch coil spans only 90 degrees, which would make sense because if n equals 2, a rotor pole pitch is going to be 90 degrees. So suddenly bars 1 and 2 would span a complete pole of the stator field and would look like one coil. And bars 3 and 4 would look like a second coil. And so this looks like a single phase winding. There's no separation between the current in these two coils. Now, n equals 4. This corresponds to the case up here when we expect to have no current. So let's just take a look at how this appears as voltage phasors. And we can see that indeed each of our rotor bars experiences a voltage source that is in phase. So that means that we're going to actually have no net current flowing because each of these rotor bars has the same phase angle of voltage source. Okay, continuing to develop on this example rotor. Now, what I want you to do is take a two pole pair air gap field that's rotating at the speed omega s, and assume that you have a stationary rotor. Plot the air gap field B delta and the current linkage produced by the rotor when omega t is equal to 0. And assume that zeta r is equal to 45 degrees. This type of angle for the rotor load impedance would correspond to a high value of slip. As your slip is approaching 1, your rotor impedance will be getting larger and larger because the frequency seen in the rotor is increasing. So go ahead, give this a try, and resume watching when you're ready to see the solution. The first thing I want you to note is that in this case, where we've got a two-pole field, we're talking about n equals 1. So it's a one-pole pair field. And since omega t equals 0, our expression for our air gap field just reduces to this. We have b delta times the cosine of alpha. We've got a stationary rotor, which means that s is equal to 1. Although for our case, when we're talking about omega t equals 0, that didn't really matter. We are also, we can then write an expression for the current in any arbitrary bar of our rotor by using our results up here. And so we know that we're going to have this expression for our current, since we've got zeta r is equal to negative 45, this is equal to 0, and then we've got our rotor phase angles here. And so when we write out the expression for our individual bars, we can again color code it based on the equivalent full pitch coil that we're seeing. So I'm mapping that. Here's green coding is up here for bars 1 and 3. Here's green coding for bars 1 and 3, right? Here's purple for 2 and 4, and that was what we had recognized up here was the case. And this expression for current, we can obtain it by solving this equivalent circuit up here, or we could also just recognize that we had summarized that up here as one of the key results. So now we're going to go ahead and plot the solution. And so initially we'll start with plotting our air gap field, and so you can see here's a plot of that. I've labeled the rotor bars on here. So starting at the leftmost, you've got bar 1 occurring at 0 degrees, then bar 2, bar 3, bar 4. And I've labeled the direction of the current in each of these rotor bars corresponding to our explanation up above. And so at this point, this is just a standard current linkage plot. If you know that at this location you've got a slot carrying 0.7 0.7 per unit current coming out of the page, you know what to do in terms of making your current linkage plot, right? And then this has got 0.7 current linkage going into the page. And remember that this sign convention here is opposite of what we had for our stator winding unit, because we're using a generator sign convention, which means that we've got positive current coming out of the page, because coming out of the page is the positive terminal of our motor, of our coil. And so if we do that, we end up with this blue plot. And so you can see, sure enough, if you look at this blue current linkage plot, it looks like a two-pole machine. And it will create a two-pole field. Interestingly, we can note that the current linkage fundamental appears to be lagging the fundamental of our magnetic field by 135 degrees, which is equal to 90 degrees plus our rotor impedance angle. And this is a neat observation. We'll formalize this more in a couple of videos, but I want to point it out now to get you thinking about it, that there is a relationship between the current linkage, or the field produced by our rotor, and the field that links the rotor. So B delta is our air gap field that is linking our rotor, and then our current linkage here, theta r, is of course what's produced by our rotor, and that would produce a field that is equal to mu naught divided by delta effective times theta r. So we can see that we can relate the angle of the field produced by the rotor to the angle of the field that is linking the rotor, and that angle is going to be 90 degrees plus our rotor impedance angle. So next, I want you to repeat this exact same example, but now have our rotor angle equal 0. And this is going to be true as S goes to 0. When you have no slip, if you look at your rotor expression for your rotor impedance, if you have no slip, if S is equal to 0, then of course the angle of this expression is going to be 0. So go ahead, do that. I recommend you plot it down here below where your previous solution was for easy comparison. And when you are ready, please resume watching. And before we make the plot, I want to point out what our rotor bar terminal current is going to be, what our rotor bar current is going to be. And so when zeta r is equal to 0 degrees, we're just going to get this expression. We know that because we've already written out up above that our rotor bar current is equal to this. Well, this right here is gone, that's equal to 0. This is gone, that's equal to 0. And so the only angle we have left in this expression is the location of each rotor bar. And so for bar 1, which we're saying is located at 0 degrees, we're going to get IR hat. For bar 2, we're going to get 0. For bar 3, we know is going to be the opposite of bar 1. Bar 4 is going to be the opposite of bar 2. And so we can now go ahead and make our plot. And again on here, I've sketched our rotor bars and the location they're occurring at. And you can see that in bars 2 and 3, we've got no current. And then bars 2 and 4 have no current, but bar 1 and bar 3 have current, and so we again get a two-pole field that looks quite different harmonics, right? And that's because that we are using a 4-slot rotor, and so there's a lot of rich harmonic content in a 4-slot winding. Again, we're noticing that the peak of our rotor current linkage lags the peak of our air gap field by 90 degrees plus zeta r, but zeta r is this time 0, so it just lags it by a total of 90 degrees. Now, at this point, we've observed quite a few nice things. We've observed this angle of separation between our rotor current linkage and our stator and our air gap field. We're observing that when we change our rotor current linkage, when we change our rotor angle, or equivalently, if we were to change omega t, we're able to see how this wave produced by the rotor is able to shift around in the air gap. And we're also noticing that this wave has got a lot of harmonic content. It does not look very sinusoidal. And so I want to just point out at this instance that this 4-slot rotor is not a practical induction motor design. Don't design an induction motor with 4 slots. It's far too low of a rotor bar count to give you a reasonable design. In fact, in this whole example here, we're not going to look at rotor bar counts that be representative of an actual induction motor, because it would take too many bars. We need like 18 bars in the rotor, and that's too hard on our hand to sketch all that quickly in example problems. So we're going to study rotors with fewer rotor bars to try to point out these kind of salient details of the induction motor and the key observations that we want to make and understand how this structure is functioning. Okay, so that concludes this part of the example. Now let's move forward and let's repeat part F for a 4-pole air gap field. So that is, we're going to redo this problem up here, but we're going to do it for a 4-pole field. Go ahead and give it a try, and when you're ready, please resume watching. Alright, so I've sketched some diagrams here and equations. I want to point out before we go through those that corresponds to this row in our table up here. That's when n was equal to 2. And so we expect to see 2 single-phase coils. In this case, n equals 2. Here's our air gap field. It's got a 2 up here, and so we can plot it here. We should see it cycle twice, which we do. And then we can again go and solve our expression for our rotor currents, which we've got down here. And indeed, we are seeing 2 coils that are in phase with each other. So this is one coil down here. Now coil sides 1 and 2 make up that coil, and coil sides 3 and 4 make up the second coil. And when we plot our current linkage, that is in fact what we see. So this is interesting. We see that we can take the exact same rotor, but excite it with an air gap field with a different number of poles, and the rotor produces a new number of poles. That is, if we take a rotor, we excite with a 2-pole field, we notice that the rotor produces a 2-pole field. If we take that same rotor and we excite it with our 4-pole field, suddenly the field that is produced by a rotor has 4 poles. Next, we're going to do this, but for the 8-pole field. And if you recall, that is this third row in our table, and we expect there to be no current linkage, or no current flowing and no current linkage produced. So please go ahead and give that a try, and resume watching when you're ready to see the solution. And we've got our solution here. We can see that when we plot our air gap field, that it always has no flux linking the rotor, which is what we expect. So since there's no flux linking the rotor, or in other words, since each of the rotor bars is exposed to the magnetic field at the exact same point, then there can be no voltage induced, no current induced in the rotor. Next, let's consider an 8-slot rotor. For a 2-pole air gap field rotating at omega s equals omega t again, I want you to do the same thing that we've been doing so far. So omega s equals omega t, we've got a stationary rotor. Plot the air gap field, B delta, and the current linkage produced by the rotor when omega t equals 0. This time, assume that your rotor impedance angle is 22.5 degrees. So we've been doing a lot of practicing to get to this point with a 4-slot rotor. I'd like you to please go ahead, give this a try for the 8-slot rotor, hit the pause button, and press play when you're ready to see the solution. So just like before, we've got a 2-pole machine, a 2-pole field, so n equals 1. We've got this B delta expression. You can see I've plotted that below. And then I've gone ahead and calculated the current in each of the rotor bars. And I've again identified rotor bar pairings which act like a complete coil. And so it turns out that in induction machines where you have an even number of rotor bars per pole pair, you can always identify pairs of rotor bars that act like they are a complete coil. If you have an odd number of rotor bars per pole pair, then the story is a little bit more complicated, but you can pretend that this is true still. Obviously, if you have an odd number, you don't have a return coil side that's 180 degrees electrically opposed to where your first rotor bar is, but it turns out that return coil splits between 2 other rotor bars. That's a little bit more nuanced. You can explore that in your own time or come talk to me in office hours about that. But in this case here, we're considering a rotor structure that has an even number of pole pairs per pole, and or an even number of rotor bars per pole pair, and so we get this behavior. And that is going to be true throughout our analysis unit. So now down below, I've gone ahead and sketched the rotor current linkage, and you can see that we get a much more sinusoidal looking current linkage. It again is lagging our air gap field by 90 degrees plus our rotor impedance angle. And so that concludes this example. So in this video, we have reviewed several examples where we calculated the induced rotor voltage and currents in a cage rotor and the corresponding fields. We summarized our key results from previous videos, and we used those in this analysis. We studied a QR equals 4-slot rotor, and then finally a QR equals 8-slot rotor with different number of pole pairs for the stator field excitation. Again, both of these examples are trivially simple. You'd never design an induction motor with only 4 slots or 8 slots unless there was some extenuating circumstance. Even this 8-slot rotor, which looks like a much more sinusoidal air gap field, this is still too much harmonic content in the machine. You're going to get torques you don't want to have there, which are going to cause problems in your torque slip characteristic. We'll talk more about that in a later video.